Hi, my name is Lawrence Hahn, and this is my project titled Designing of Prompts for Hate Speech Recognition with In-Context Learning. So here is the presentation overview. First, I will discuss the problem. Then I will talk about the literature review for both in-context learning and hate speech recognition. Afterwards, I will talk about my approach and the experiments, and I will finish with the conclusion and future work. So first, the problem. So large language models like GPT-3 have shown impressive performance on new tasks never trained before by simply doing the inference with a prompt. This type of inference has been referred to as in-context learning. The prompt usually consists of a new task description, a few training examples, and one test instance. Previous studies have also shown that the design of the prompt will impact the final performance. Therefore, we will focus on two problems in this presentation. The first is how we can design effective prompts for hate speech recognition with GPT-3 in context learning. The second problem is how we can ingest our prior knowledge to further help GPT-3 through the design of the prompt. So here is the literature review for in-context learning. So traditionally, we have used the pre-training slash fine-tuning paradigm, which is a machine learning approach that involves first training a model on a large general purpose dataset. Then we fine-tune the parameters of the pre-trained model for a specific downstream task using a large thousands to hundreds of thousands corpus of labeled data. The model is then continuously trained via repeated gradient updates. This traditional paradigm leads to a strong performance on many benchmarks, but it requires a new large set of datasets for each task and is not applicable for giant models. The new in-context learning paradigm does not require any training or optimization of the model parameters in the adaptation step. We simply give the model a task description as well as a few examples as the input at an inference time. In terms of prior work, in-context learning has been the focus of significant studies since its introduction. Prior work proposes better ways of formulating the problem, choosing labeled examples for the demonstration, meta-training with an explicit in-context learning objective, and learning to follow instructions as a variant of in-context learning. At the same time, some works report brittleness and oversensitivity for in-context learning. So here we have the literature review for hate speech recognition. There is no commonly held definition of hate speech. Different legal jurisdictions have different definitions, as do different companies and other groups. Detecting hate speech is difficult because the definition of hate speech varies, depending on a complex intersection of the topic of the assertion, the context, the timing, outside events, and the identity of speaker and recipient. Moreover, it is difficult to distinguish hate speech from offensive language. Hate speech detection is of interest to academic researchers in a variety of domains, including computer science and sociology. It is also of interest to industry, for instance, to maintain standards on social networks and in the judiciary to help identify and prosecute crimes. There has been a large amount of research focused on detecting hate speech. As part of this process, various hate speech datasets have been created and examined. As to the prior methodologies, some are listed here. First, using convolutional neural networks. Second, using short text data augmentation. And third, using BERT. So before we talk about the approach, let's talk a little bit more about in-context learning. In-context learning is a recent paradigm in natural language understanding where a pre-trained large language model directly performs a new task without any update to its parameters by taking a test instance, new task description, and a few training examples, input, which are also known as input label pairs, and as its input. So here is our approach. The prompt consists of three components: a task description, a training example, and a test instance. The task description is a written or verbal explanation of the goals and objectives of a particular learning task. It typically includes information about the data that will be used for the task, the types of predictions or decisions that the model is expected to make, and any constraints or limitations on the model's performance. In this example, the task description is classify the following texts into hate speech or not, which is what we want the large language model to do. A training example is a set of data that is used to teach a model about a particular concept or task. This set of data typically consists of input data and the corresponding correct output, which is known as the ground truth. The model uses these training examples to learn how to produce the correct output for a given input. In this example, the training examples provide a sentence and its classification as hate speech or not. So we have, you should know women's sports are a joke. That's classified as hate speech. And do you do the world a favor and pour some bleach into the glass? And that's classified as not. Finally, the test instance is a piece of data that is used to evaluate a trained model. This data is typically different from the training data that the model was trained on and is used to assess the model's performance on new, unseen data. The test instance is presented to the model, and the model's output is compared to the known correct input, which is also known as the ground truth, to evaluate the model's performance. In this example, the test instance is a new sentence the model hasn't seen before. Feminism is a very terrible disease. As we can see, the large language model correctly classifies the test instance as hate speech. We plan on studying the first two components of the prompt individually for better performance: task description and training examples. On top of that, we want to examine how we can ingest our prior knowledge into those components to further improve performance. For our dataset, we used Ethos Online Hate Speech Detection Dataset. It is built from YouTube and Reddit comments, validated through a crowdsourcing platform. It has two subsets, one for binary classification and the other for multi-label classification. The former contains 998 comments, while the latter contains fine-grained hate speech annotations for 433 comments. In the binary dataset, comments are classified as hate or non-hate based. In the multi-label variant, comments are evaluated on measures that include violence, gender, race, disability, religion, and sexual orientation. We use the binary dataset to evaluate the performance of any prompt designs. However, we will also study how to use the extra information in the multi-label dataset to build prompts. This is the outline of our experiment, consisting of three different studies. First, the effect of the number of training examples. Second, the quality of training examples. And third, ingesting our prior knowledge. So let's start with the effect of the number of training examples. We examine how a different number of input label pairs in the prompt can affect the model performance. Results are reported in the graph below. First, Text DaVinci 002 model already shows a very strong zero-shot learning capability, which is the ability to complete a task without having received any training examples provided in the prompt. Providing a few training examples in the prompt doesn't help to improve the model performance. Second, only after the number of training examples reaches a decent amount do they start to boost the model's performance. However, this boost does not increase as the number of training examples increases. Therefore, in the next experiments, the number of training examples in the prompt is set as 16 unless specified otherwise. As you can see in the graph, the accuracy is around 0.84 with 0 to 8 training examples. Between 8 and 16 training examples, the accuracy starts to increase. However, the accuracy starts to plateau as you go above 16 training examples. Now, we will also examine the quality of the input label pairs when the number of them is fixed. More specifically, the comments in the Ethos binary dataset have scores between 0 and 1, which represent how confident the raters are about their labels. Therefore, it would be interesting to know if higher confident ones, which are the comments rated 0 and 1s, since they're the ones that are sure of if they're hate speech or not, can help the model more than lower confident ones, the comments rated around 0.5, since those are the ones that are hard to determine, or vice versa. Using the comments rated around 0.5 is known as hard example mining. Hard example mining is a technique used in machine learning to improve the performance of a model by focusing on the most difficult examples in a dataset. This involves identifying examples in the training data that are hardest for the model to predict correctly, and then using those examples to train the model. This can improve the model's ability to generalize to new data and can help it to achieve better performance on a variety of tasks. It is well known that hard example mining can improve machine learning models, so expect that using this technique will help improve the quality of GPT-3. However, using hard examples in the prompt shows no obvious performance gain compared to using the easy ones, as you can see from the information in Table 1. Now, let's talk about how we can ingest our prior knowledge. From Table 1, we can find that even though the model can achieve very high recall, the precision still has a lot of room for improvement. To achieve this, we explore other avenues beyond the training examples. In the Ethos multi-label dataset, the hate comments are further labeled based on if they have offensive content about violence, gender, race, disability, religion, or sexual orientation. This extra information actually represents our prior knowledge about what aspects to evaluate when we, as human beings, classify one comment as hate speech or normal speech. Therefore, it would be valuable to study how to ingest such prior knowledge into the in context learning paradigm. We studied three ways to ingest above prior knowledge. First, instead of providing examples with binary labels, hate speech or not, we can further divide the hate speech labels into finer level labels based on the underlying offensive content. Hopefully, the model can learn what perspectives to evaluate through this finer level label space. Now, the task description becomes classify the following texts into gender offensive, race offensive, national origin offensive, disability offensive, religion offensive, sexual orientation offensive, or not. Second, instead of asking the model to generate classification labels such as binary or multiple ones, we can ask the model to generate the chain of thoughts before reaching the conclusion. The following shows one training example in prompt with this approach. You should know women's sports are a joke. This is hate speech because it is gender offensive for women. Third, directly instructing the model about the perspectives to use in the task description. Classify the following texts into hate speech or not. For hate speech, consider if it is gender offensive or race offensive or national origin offensive or disability offensive or religion offensive or sexual orientation offensive. Results are reported in Table 2. Using more informative instruction seems to be the most effective way to ingest our prior knowledge into the model and thus achieve further performance improvement. So, in this paper, we studied a number of ways to design effective prompts for hate speech detection with GPT-3. We find that the number of training examples in the prompt matters. We also discovered that providing informative instructions is more effective than other ways to ingest our prior knowledge into the model to further improve its performance. Now, I'm going to briefly discuss about our future work. So, one limitation of our work is that the training examples in the prompt are fixed for any test instance. So once we decide the number of them and how to choose them. So in the future, I think it's worth studying to use different sets of examples for each test instance. That is the end of my presentation. Thank you for listening.